The creation and study of maps, such as those we've been looking at in class, is called cartography. The concept of the map is thought to be as old as the 7th century BC, though the early drawings that we believe to be maps look hardly anything like we know today as a map. Since those early wall paintings found in modern day Turkey, maps have been used to show everything from the motion of the stars in the sky to a soul's path from heaven to hell, to our modern understanding of the surface of the earth. One thing all of these maps have in common, though, is that at their heart, they are an attempt to display complex physical systems in a simple two dimensional form. The maps that we are going to look at today represent the attempts of about 500 years worth of cartographers to accurately represent the size and placement of Earth's land masses, which exist in three dimensions, on a two dimensional drawing. One way cartographers do this is to imagine a light that shines through the surface of the Earth, casting an image onto a screen of different shapes. Much like the way a movie projector casts a light through a film to display a movie in a theater. Because of this analogy, we call these different styles of maps projections. There are many different projections, of which we'll cover a few in this video. The first one we're going to look at right here is called the Mercator projection. It's probably the one that we know best in today's world. It was developed in about 1569 by a Dutch cartographer named Gerardus Mercator, hence the name. It was unique at the time because it represented north as up and south as down. This is surprising to us because we always think of north as up and south as down, but this was actually the first one to do so. It was pretty standard for navigation, which was a major deal for the Dutch at the time, who were large traders. The reason for this is that in a local area, in a small area, the directions and the shapes of coastlines are very well preserved. So a shipmaster could look at the map, look at the coast, and they would see exactly what they are looking at. The Mercator projection is one of a style of projections that is called the simple cylindrical projection. The way all these projections work is they imagine a movie screen, essentially, that is cylindrical and wraps around the globe of the Earth. It then imagines a source of light at the center of the Earth, with the surface acting sort of the film in a movie projector. When the light source hits that film, it casts a picture onto the screen, and the cylindrical projection, the Mercator projection, is what we would see if we were looking at that screen. You can see here the way that cylindrical projection would be wrapped around the globe and ends up with a map that we are all very familiar with. The Mercator projection is not the only simple cylindrical projection. We can wrap the cylinder at a 90 degree angle from the way Mercator wrapped it, and we end up with a map that looks something like this, which looks quite strange to those of us who haven't seen it before. Notice in this projection how Antarctica and the North Pole look very normal to our eyes, while Malaysia and Indonesia up in the upper right-hand corner look very stretched, very distorted. This distortion is a major drawback of cylindrical projections. The major flaw for the Mercator projection itself is that it tends to stretch land masses that are near the poles. If we look at the size of these circles on this particular picture, we can see just how stretched the map is. For a completely unstretched map, all of the dots would be exactly the same size. But as we look at this picture, we can see how large the dots are at the top and bottom and how small they are in the middle. All right. Antarctica in this projection is enormous. Greenland is quite large. If we look at what we might call a corrected Mercator projection, like this one, we can actually see the actual size of different parts of the Earth's land masses. Greenland, for example, up the top, in a Mercator projection, appears to be about the size of Africa, if not larger, when in reality, Greenland is only slightly larger than Alaska and is only 1/14 the size of Africa. So it is enormously stretched in this Mercator projection. Russia, while still being the largest country on the face of the earth, is actually much smaller than it appears. It's very comparable to the country of China or Canada. The next projection we're going to look at is called the Good Homolocene map. In 1923, John Paul Good, a cartographer from Minnesota, created this projection to try to counter the distortions seen in the Mercator projection. You can notice it's sort of similar in its placement of land masses and things like that. It's still generally cylindrical. However, there are big cuts taken out, like the one between Greenland and Russia, and the one in the Indian Ocean, Atlantic Ocean, Pacific Ocean. These cuts are taken out to ensure that we don't get nearly as much distortion near the poles. So Russia appears much smaller in this version. Greenland appears much smaller. And we don't see nearly as much land mass down at the South Pole, down in Antarctica. This version of the Good Homolocene projection map is the land version. Okay, you can see at the top there where it says land. This version emphasizes the land masses, and each land mass gets its own sort of slice of this particular map, other than Antarctica, which gets cut between all four. Now, there is a different version of this called the ocean projection, where each ocean is emphasized. All right, you can see where the land masses now are being cut rather than the oceans are. This is the same projection. It is slightly a different shape, but the idea remains the same. It is still trying to refrain from distorting areas at the poles while keeping the shape of land masses the same. Now we're going to look at some projections that imagine a screen that is not a cylinder, but a different shape. The first one we're going to look at imagines a screen that is shaped like a cone. This is referred to as a conic map projection. So we create a map like this by imagining the view from an observer that is some distance above the Earth's surface, looking down on the surface from above. These maps, though a very different shape than the one we are used to, are actually very accurate for recording the shapes and sizes of land masses that are at mid to high latitudes in this particular case. So latitudes between about 45 degrees and 90 degrees. In other words, latitudes from like upper Canada to the North Pole. They become increasingly inaccurate as you move beyond those latitudes, particularly as we get close to the equator. Looking at this particular one, we can see that Africa appears to take up nearly a full third of the globe on the right-hand side. These maps are typically very regional. They don't actually often show the entire map. Now, they do sometimes show the entire globe, such as this one right here, where we can see Antarctica vastly distorted as it wraps the entire way around the globe. These maps, like I said, are very good for small areas, local areas. They are generally not particularly great for large areas. The goal of a map like this would be to use it to determine a straight line from one point to another in a relatively small area. Maybe you were flying from Russia to Canada or something like that. You wouldn't want to use this to try to fly from the North Pole to the South Pole. The next one we're going to look at is sort of a modified conic. This is called the Bond projection. It's often called pseudo-conical. meaning that it's similar to the conical projections we just saw. Now, it does have some slight differences. You can see how it's much more rounded in its overall shape. One thing that it does do very well is actually show land masses in a T shape. So if you look at the size of the dots in this image, the dots down the middle are of about the same size, and the dots in a line around the upper third of the top of the map, so right across Africa, across Asia, the Pacific Ocean, and over to Mexico, you see those dots are all about the same size. Those areas do not appear distorted. They are about the right size and about the right shape. As you move away from that T shape and look at the dots in like Australia or South America or up into Russia and Canada, those dots begin to be misshapen and distorted. You can especially see this at the North and South poles, where they don't even look like dots. Next, we're going to look at what is referred to as a mnemonic projection map. The mnemonic projection map looks relatively similar to a conic, except instead of having that cut at the top and the point at the bottom, we see actually a full circle. A mnemonic projection map is very accurate at the point at the center. These maps are used for finding shortest distances between two places on coasts often. They are quite good at that, and beyond that, they don't see a whole lot of use. So it's mainly sort of a shipping logistics sort of map, not something that you would often see outside of an industry like that. The way we create a mnemonic projection map is to imagine a flat plane that touches the Earth at a single point. We say it is tangent to the plane or tangent to the globe. All right, so where the conic observer was above the surface of the Earth, the mnemonic observer is actually on the surface, and the plane touches that globe at a single point. All right. When looking at them, the central point is very true to life. The shapes are preserved, the sizes are preserved, but as we get further away from that point, the shapes become very distorted. So here you may not be even able to tell, but we are looking at the North Pole. Greenland sits just down and to the left from that center point. The North American continent is the small landmass to the left. Asia is the landmass to the right. Europe is down below, with Africa down at the very bottom there. All of those landmasses are looking really distorted, except for the ones very close to that center point. Up next, we're going to look at the Atoff projection map. This one was created in 1889 by a cartographer named David Atoff, and it is one of a type of projection that is called azimuthal. As in azimuth is a mathematical term, and the point of a map like this is that it describes the direction a person would need to travel to get from point A to point B using a point C as a reference point. So it's for finding the straight line directions that you would need to get to different places. There are many azimuthal projection points. This Atoff projection is just one of them. The Eckert is another version of an azimuthal projection. If we look at this one, we can see that this one has horizontal lines of latitude, whereas on the previous one, the Atoff, the lines of latitude curve as we get to the far left and right. The Eckert also features a straight prime meridian right in the middle, while all of the lines of latitude and longitude curve. They curve more and more as you move left and right, though less so than the ones in the Atoff. The next projection we're going to look at is the vertical perspective projection map. This one may be relatively familiar to you guys. This one is the most photographic projection map. This vertical projection map does not attempt to actually show all land masses. It shows only what you would see if you were actually in space and took a picture of the Earth. So if you have ever seen a picture taken by an astronaut of our planet, this is exactly what that picture is going to look like. Up until this point, all of the projections have been a relatively familiar shape, though the conic and boon projections got a little weird there. The final three projections we're going to look at take the idea of the map and really make you have to wrap your head around what's going on. Now, the first one we're going to look at is called the World Cube Projection Map. The cube projection takes the spherical globe and turns it into a six-sided cube. You can see how if you folded this together, it would make a cube rather than a circle. The sides are split, with one side going to the North Pole, one side going to the Antarctic, or the continent of Antarctica, and the other four being split between the remaining land masses of the globe, much like a Mercator projection. There isn't really a whole lot of call to use this particular map. This is more of just a thought experiment than anything. But it still shows everything that is on the globe, though there is definitely distortion and some repeating of land masses. You can see that you see Europe and Russia sort of on two different sides. The next one we're going to look at is the Fuller projection map. This is also known as the Dymaxion projection. The idea with this one is that you take the sphere of the Earth and you project it onto an icosahedron, which is a 20-sided shape. If you've ever seen a 20-sided dice, that is the shape that this projection imagines. Due to its shape, the projection has less distortion, particularly on the edges of the individual triangles, though there is some distortion towards the center of those triangles. Not a whole lot, but there is some. There's no cardinal directions on this map. There's no such thing as north, south, east, or west. There is, in the words of the creator, there is only in and out. The creator of this map was a gentleman named Buckminster Fuller. This map was created in the mid-20th centuries, in the 1950s. It was improved over the following decades. And the reason that Buckminster Fuller wanted to make a map that included no north, south, east, or west was because he wanted to avoid the cultural bias of traditionally European cartographers that emphasized the size and importance of European countries. That's one reason why the European countries are so distorted in projections like the Mercator projection, while Africa remains about the same size, appearing comparatively much smaller than it actually is. Africa is enormous in comparison to Europe, but on the Mercator projection from the beginning of this video, it appears to be about the same size. Mr. Fuller wanted to avoid that cultural bias with his map as much as possible. The next map takes its inspiration from that Dymaxion map. This one is called the Orthograph projection. This is actually the most recent projection of the ones that we've looked at. This one was created in 1999 by a Japanese architect by the name of Hajime Narukawa. The way he created this map is kind of crazy. He divided the Earth's surface into 96 triangles. He transferred those 96 triangles onto a four-sided polygon called a tetrahedron. Basically looks like a three-sided pyramid with a bottom. He then unfolded that shape, the tetrahedron, into a rectangle. And this is the map that came out of that. It's thought by many to be the most accurate map ever made. It does a very, very good job of maintaining the shapes of coastlines and the relative size of countries and continents. And unlike most projections, it does that for the entire globe. It's not going to emphasize one part of the globe or another. All parts of the globe are very well done in terms of accuracy for both size and position. One other thing about this map that's a very big plus for it is that it also allows Antarctica to be shown true to size, so its actual size in comparison to the rest of the Earth's continents, and in the correct position. Uh, that is one thing that most projections have issues with. If you remember back from the beginning, things like the Mercator projection or the Good projection had Antarctica either stretched across the entire bottom of the projection or cut into many small pieces and just kind of thrown down at the bottom. This projection is very good at showing the actual size, shape, and location of Antarctica, something that's often forgotten. It does have some issues up in the northern parts of this map. Land masses up there like Canada, Russia, Greenland, they are stretched a little bit in much the same way that the Mercator projection stretches those land masses, but it's not nearly as pronounced a stretching as we get with the Mercator. One thing that does make this map really hard to read for people used to other maps like the Mercator is the way that the lines of latitude and longitude seem to almost randomly bend, and they never appear to be truly parallel with their neighbors. We're used to lines of latitude being straight lines from east to west across a map, while lines of longitude all bend relatively the same and come together at the north and south poles. In this map, those lines of latitude uh, are bending all over the place, and the lines of longitude don't meet at a single point. They meet at sort of a circular shape up there in the top and top left area. So it looks strange, but it is thought to be one of the, if not the most accurate map ever made.